So we finished up last time talking about confidence intervals. Okay. Someone tell me what we're trying to do with a confidence interval. Why are confidence intervals sort of why does Josh like confidence intervals? What do you think, Allie? You're my student. Why do I like confidence intervals?
I mean, it provides like more of like a range of values rather than just like one value.
Yep. Yep. So confidence interval gives us a lot of information. In the next set of slides, we're going to start to get into inference tests, and hypotheses. But the issue with inference tests is they just tell us whether or not some parameter of interest is likely to be zero, right? And a lot of times, most times, whether or not something is zero is not an interesting question, right? We want to know, well, how much different than zero is it? How sort of what's the actual parameter? And then wanting to get some idea about the level of precision of our estimates. Some of our estimates are very, very good, and we have very, very tight intervals. Some of our estimates are really poor. They might not include zero, but that doesn't mean it's a good estimate. Still a lot of ambiguity in terms of the things that we're trying to interpret. And so our confidence intervals not only tell us give us a point estimate, tell us whether or not our data support zero as a probable value for whatever we're looking at. But then it also gives us, say, a level of sort of a sense of precision and sort of upper and lower bounds for different types of things. So if we're looking at confidence intervals, again, three pieces of information going on here. If we're talking about confidence intervals around the mean, we've got our value of our mean or our point estimate. We've got our standard error. We're going to talk about that a lot more in this next set of slides. And then our a test statistic or a z-value for a chosen level of estimation. Okay, these are just good values to just have memorized, so you don't have to keep looking them up. If we're talking about a z-table, 90% confidence interval associated with a value of 1.65, 95% confidence interval, this is our most common, 1.96. And then our value of 2.58 for 99% confidence interval. Once we get into screenings, 3.29, that's associated with a probability value of 0.001. So we'll just use these enough that these start popping in. To calculate our confidence interval, we're just going to take our mean plus or minus our z-score for our chosen level of estimation, multiply that by our standard error. It's going to give us a confidence interval. So easy peasy stuff to do. Okay, so let's go through an example. So here, we've got a scenario where we've got a former librarian at a local library has claimed that on average, books in the library were 20 years old. Okay, new librarian comes in, and new librarian, this guy doesn't play by the rules. He's got his own ideas, his own agenda. He's like, I don't care what your estimated age of the books are. Old guy, I want to do my own estimation of the age. I don't like your 20-year estimate. So what he does, right, is he goes through and collects 150 books. And let's assume that this is a random selection of books, records the publication date. And what the new guy finds is that he's got a mean age of the book in the sample 23.8 years with variance 67.5. Okay, so based on this information, what we want to do is we want to calculate a point estimate for the true age of the books, calculate a 95% confidence interval, and then we want to sort of provide some interpretations about this. Okay. So first thing, number one, Riley, we're looking at point estimate for a true age of the books. What's my point estimate for the true age of books based on the material here?
23.8.
Perfect, right? To the best of my knowledge, based on the 150 books that I've collected, and let's say we've done a good job of randomly selecting books, my best guess for the actual population value is 23.8, right? Now, Riley, how confident am I that that the actual true average age of books in this library is exactly 23.8 years?
This could be wrong, but I feel like not very confident.
Yeah, Yeah. If you sort of pushed me and said, I want you to bet $1,000,000 that the exact value is 23.8, I would say, no way, right? Because I know it's not exactly. It'll never be, it may be very, very close, but it's never going to be exactly 23.8. So what I want to do is, say, okay, this is what I've guessed, but here's my tolerance. This is sort of, at least from the data that I've collected, this is what what I think it would be supported, at least by the data that I've collected. And this is where our confidence interval comes in, okay? So I've gone through and didn't want to take a bunch of time scrolling over sort of my little writing pad and stuff like that. Microsoft Paint is a powerful, powerful program, but we'll just go through and it did the handwork for you here. Okay, so what we found, if we go down through and we take a look, point estimate for the average age of books in the library, 23.8 years. It's just our mean, right? But then what we need to do is we want to go through and we want to calculate a confidence interval. So I've got a mean value of 23.8. My sample variance is 67.5 with a sample of size of 150. Okay. So first thing I've got to do, Erica, is variance what I want to use right here? So in my problem here, I recorded the variance of my sample. Do I want to use the variance, or do I want to first change that into something else? Okay, yeah, we'll get to standard error. What else can we get from variance just right away? That's maybe a little bit easier to interpret. Someone help her out?
The standard deviation.
There we go. Standard deviation, right? Remember our standard deviation, variance is super important. It's used in a lot of calculations, but variance isn't terribly intuitive. Our standard deviation, we can think about this as the average difference between any randomly selected score in a distribution and our mean, right? So what we're going to do first is, so we've got our variance estimate. We're going to take our variance estimate, take the square root of our variance, gives us a standard deviation. Okay, so we know based on this calculation that in my 150 books, on average, right, if I just randomly pull a book from that sample, it's going to be on average a little over 8 years, plus or above or below the my mean value of 23.8. Okay. So again, standard deviation is just giving us a measure of variability. So I calculate my standard deviation, and then I go down through with my standard error formula, right? Standard error is just the standard deviation divided by the square root of my sample size. So I take my standard error, my standard deviation, 8.216, divided by the square root of my sample size, 150, gives me my standard error. Okay. Now my standard error, we're going to talk about this in the next set of slides. Think about your standard error as sort of telling you how much across repeated samples do you expect your mean value to jump around, right? And here, my standard error is this, let me see, Brittany, does this look like, if I were to resample this library book, grab a new sample of 150, and then a new sample of 150, and then a new sample of 150, and every time I'm expecting my sample to jump around by 2/3 of a year, is that a lot or a little, relatively speaking?
2/3 of a year is a lot, I would say.
If we're talking about the average age of books in a library?
Oh no. Well, I mean, I don't know exactly what 0.671 would like. I was writing down what you said standard error means, so it tells you how much you think your mean will move around. So 0.671, I guess, for books, no. But
Yeah, probably not, right? If I'm thinking about books in a library, right? And I know that on average, any given book that I pull out of this sample was about a little over 8 years from the mean, right? So if I've got a sample where I'm expecting across replications that my mean estimate is going to jump around 2/3 of a year, say, that's not too bad, right?
Well, yeah, I understand. Yeah, it's not bad.
Okay, cool.
I get it.
And so someone tell me, so I'm thinking my sort of precision at just looking at my standard error seems pretty good. Why is this? What's contributing to my pretty impressive standard error here? What do you think, Natalie?
Um, I guess the number of books.
Yeah.
I'm not quite sure.
Nope, you're exactly right. How many books do I have in this sample?
150.
Yeah, that's a pretty good size sample, right? I don't know how many books are in this library, but 150, that's a pretty good sample, particularly if it's random, right? And so what we get, Natalie, as my sample size increases, what happens to my standard error?
It decreases.
Yeah, it decreases. And why does that make sense? As my sample gets larger, the amount that I would expect my point estimate to jump around from sample to sample starts to get smaller and smaller. Why does this make sense?
Because there's a larger number of books to kind of cover that variation.
Yeah, exactly right. The bigger my sample, right, the more stable that estimate is going to be. As my sample gets larger and larger, my standard error decreases because I'm expecting, if I've got a really big sample, I'm expecting that to be a pretty good estimate of whatever I'm trying to take a look at. I'm not expecting things to jump around a whole lot. Now, Natalie, one more question. I'll quit harassing you. What if my sample was 10? Would I expect a big jumps in the average age of books if I'm only grabbing 10 books at a time?
Probably slightly bigger jump.
Yeah, actually, quite a lot bigger jump, right? Because with only 10, even if I have a representative sample, if I'm only grabbing 10 books, the likelihood of me grabbing 10 books that are all pretty new or pretty old or sort of jumping around starts to get pretty big, right? So what we've done here is we've got a pretty big sample, right? And we see that when I go through and I calculate my standard error, I'm expecting just across replications based on the data that I've collected, I'm expecting my any repeated estimate of my mean to maybe jump around by about 0.67 years, which in the grand scheme of age of library books is probably pretty small, right? So I go through. Now at this point, I've got everything I need to calculate my standard or my confidence interval. Got my point estimate plus or minus my precision, my level of estimation here. Robert, where did I get 1.96 from?
That 1.96 you that was that's the z-score associated with the 95%
Yep.
confidence interval.
Is that score going to change for any 95% confidence interval I calculate with a z distribution?
No.
No, it's always going to be 1.96, right? As long as we're calculating 95% confidence intervals and then multiplied by my standard error. And if I do this, I get a confidence interval for my point estimate of 23.8, 22.5 at the lower limit, 25.1 as the upper limit. And then this, my margin of error, this is plus or minus 1.32, okay? Margin of error is just this piece, right? So it's your confidence level multiplied by your standard error. This is saying that what we're getting, this confidence interval, we can say point estimate for the average age of books based on the data that we've collected, 22.5 to 25.1, or we could say average age is 23.8 plus or minus 1.32 years. Okay. Do people see sort of where these calculations coming from, where we're getting all this stuff?
I'm sorry, where did you get the margin of error from again?
Margin of error is just this plus or minus piece down here, right? So if I take 1.96, Riley, and multiply it by my standard error, this is just telling me what I'm adding or subtracting to my point estimate to get my bounds. Just a different way to go through and talk about your confidence interval. You can present it as a tolerance. It's the same thing as this. Okay. Other questions? Okay. So last thing we want to do with this is provide an interpretation for the confidence interval Remember, I had given you lots of different ways to go through and sort of think about or interpret these confidence intervals. This isn't a mutually exclusive list, but again, I can't emphasize enough. You'll be using confidence intervals. You'll be interpreting a lot of confidence intervals. The extent to which you can kind of play around with different ways of thinking about this or interpreting this will solidify sort of what this means, how it sort of comes in, and will help make it feel when you're doing assignments that you're not just cutting and pasting sort of stock answers that don't actually mean anything, right? So if we're going through with this example, right, I could interpret this a bunch of different ways, but some examples based on the data collected in the sample, plausible values for the average age of books in the library range from 22.5 to 25.1, right? So we're saying that my point estimate, 23.8, but based on the data I've collected, anything between 22.5 and 25.1 years would be reasonable based on the data that we've collected. Is a value of 22 years for the average age of books, is that impossible? Yeah. Is a value of 22 years based on my confidence interval, is that an impossible value for the average age of books? Nope, it's not impossible. Is it likely? Really? Yeah, well, if you're taking a look at sort of what's your lower limit of the confidence interval here? Okay, what's the lower limit of your confidence interval? No. So if looking at your confidence interval right here, what's your lower bound limit here? 22.5. Okay. And so this is the lower limit and the upper limit of what your data would support as the actual value of age of books in the library. So is 22 years impossible? No, but is it likely based on the data that you've collected? No, it's not, right? So if you're the new librarian, I'm the old librarian, I say, hey, well, I think it's actually 22. You might, maybe, but that's not supported by the data. So I don't know, like if that's the game we're playing, I don't know, why not say 50 or 3, right? What we're trying to do is say what are data supported values, okay? So we could also talk about this as data supported lower bound estimate of 22.5 years for the average age of books with an upper limit of 25. We could say results indicate a point estimate of 23.8 years for the average age of books in the library with an expected error of estimation of one plus or minus 1.3 years. Riley, this is where we're getting at where we can use the margin of error, because sometimes this is a nice way to explain things back. Yeah, we're saying 23.8 years plus or minus 1.3 kind of gives us a sense for what we're doing. Okay, so again, what I'm doing here is just giving you some different ways of sort of if you wanted to talk about it. Depending on the problem or the question, different things will maybe make more sense. Just encouraging you to play around with this a bit. Okay. So general conclusions. Remember that we're not just doing this to do stuff, right? If we go back through, we see that the whole purpose of this was to try and say, okay, old librarian says the average age of the books were about 20 years. We want to go through and see, is that reasonable, right? So if I'm going down and through and I'm taking a look, some things that I can sort of draw from this, we could say our estimate for the average age of books, fairly precise, giving our margin of error, right? So again, as Brittany noted, this standard error is not too bad. If I'm talking about average age of books in a library, huge range, a little over a year plus or minus, not too bad in terms of precision, right? So again, assuming we've got a representative sample, normal distribution in the age of books, looks like our estimates are doing pretty good, right? It's not huge. It's not saying, oh, plus or minus 15 years. That would be sort of not so great, right? We could also conclude that our former librarian's estimate of the average age of books doesn't appear plausible given the data collected in this sample. So 20, it's fallen outside of the bounds, right? Robert, is it impossible that the true age of books in the library is 20 years?
No, it's not. No, it's not impossible.
It's not impossible, right? We may have just randomly collected a weird sample that overestimated the age, but based on the data that we have, we would say that probably this guess of 20 years is not plausible, right? Now, we could also say that sort of at minimum, right? If we look at the lower bound estimate of our confidence interval here, we can get more specific. We can say that the old librarian, based on our data, has underestimated the true value of age of our library books by at least 2.5 years, right? Rachel, where did I get that 2.5 a minimum a minimum underestimation?
Well, you looked at your lower bound, and then you looked at the overall estimation, and then
Yeah. Perfect, right? And so this is just sort of adding some of the nuance here. So I've got someone who said, old person said, average age of books is 20 years. Lower bound estimate of the confidence interval for what I got is 22.5. So at minimum, like at best case scenario, you've underestimated the average age of books by about 2.5 years, but it could be anywhere to over 5 years in terms of your underestimation, right? So just thinking about using the information provided in these interval estimates carefully and sort of thinking about how do we go through, describe, talk about something, just adds a whole lot more nuance into your interpretations, as opposed to just saying, yep, it's probably not, the average age of these books is probably not 20 years. Well, fine, but then give me more, like what else is going on, okay? Anybody have questions about sort of what we did here, how we pulled this stuff together? Feeling comfortable with this? Okay, cool. Go to a second example, okay? So here we've got researcher interested in Flynn effect. Wants to know whether what the current average score would be for an IQ test developed in 1980. Can someone tell me what the Flynn effect is? I don't know if you guys have gone over that in Tara's assessment course yet, clinical students. But anybody know what Flynn effect refers to?
the tendency of IQ scores to increase over time.
Yeah, who gave me that? I was on the wrong thing. Okay,
Rachel.
Rachel, good. Okay, you got that. Yeah, so Rachel, you're exactly right. What we know is we go through and we norm and develop a test. But we have to continue to renorm those tests because what happens is we see creep. If it's normed, if this test is normed at to have an average of 100, after a while that average will start to creep up, and it's kind of an interesting phenomenon. We don't exactly know why it happens, right? And so we call this a Flynn effect. And so what we've got is a researcher interested in looking at this, right? And so what they have is an IQ test developed in 1980. And what they do is they take this sample of 180 people and they administer this IQ test that was developed in 1980. Okay. Now, Rachel, help me out. What's the mean? What should the mean of an IQ test be? Do you remember?
No, sorry.
No. Okay, anybody know what IQ sort of is normed to?
Isn't it 100?
Yep, it's 100. Okay. So what we should find, in the absence of Flynn effect, is that this test that was normed in 1980 should still, if I give it to people today, people should still have an average of 100 on this. Okay. So I give it to 100 people and find that they have an average score of 107 with standard deviation 12. Again, the population mean in 1980 was 100 like it was supposed to be. Okay, so same thing. Want to calculate a point estimate for the current population on the old test. Calculate 99% confidence interval, and then provide some interpretations. Okay, so Robert, what is my point estimate for today's population score on this test from 1980? Yeah, 107, right? Is that 100? Nope, it's not, right? So we do see some evidence for something that looks like a Flynn effect, right? We're seeing something that looks like it's an upcreep in scores, but what we want to know is see sort of how precise our estimates are, right? And this is where some of our interval stuff comes in. So again, went through and did this. If we go down through, we've got mean of 107 in our sample, standard deviation of 12. We've got score of 120, people that we tested. Point estimate of the current population score on the 1980 test is 107. But then we want to calculate our confidence interval. Here, we're already working with our standard deviation, right? So we can just plug this into our formula. We've got our standard deviation divided by the square root of my sample size. Gives me a standard error of about 1.1. Okay. Allie, can you give me an interpretation of this standard error? Kind of a practical sense.
What do you like?
Yeah, what does this standard error mean if we're thinking about it conceptually?
So it's kind of like a standard deviation?
Yeah, it really is like a standard deviation for not for the distribution, but for our sampling distribution. And we'll talk about this, right? So if I were to grab another 120 people and give them this 1980 test and another 180 and another 180, how much would I expect that mean score to jump around on average across replication sets? Yeah, about 1.1 points, right? And if we're talking about an IQ test with a mean of 100, sort of if my samples are jumping around by about a point on average, is that pretty good? Yeah, that's pretty good. Again, speaking to the size of of our sample here. Now, also my sample variance impacts my standard deviation, but really the thing that's driving that's impacting my standard error, but really what's driving it is my sample size here. Okay, bigger samples result in smaller standard error, means should be expecting less jumping around from sample to sample. Okay, so I'm going through, calculate my confidence interval, have my point estimate of 107 years, plus or minus, Erica, where did I get this 2.58 value? Yep, perfect. And if I were to go through and use my z-score to calculate a bunch of other 99% confidence intervals, would that change at all? No, it's always going to be the same, right? So here's the z-score for my level of estimation. Here is my standard error, which gives me my confidence bound here, right? And again, my margin of error is just going to be 2.58 times my standard error is going to give me 2.83. So I can say sort of lower bound and upper bound that estimates for the true population mean on this 1980s test in today's population, somewhere between 104.2 to 109.8, or we could say 107 points plus or minus about 2.8 points on that, right? People see how we calculated that? So again, possible interpretations, again, wanting you guys to sort of play around with thinking about flexibly, how do I go through and talk about this? There'll be things that you'll kind of gravitate towards just because it kind of makes sense to you, which is awesome. But do play around with sort of different ways of presenting this. So you could say, based on the available data, plausible values for the average score in the 1980 exam in members of current population range from 104.2 to 109.8, assuming normal distribution of scores. Again, notice that I'm contextualizing this and it's important, right? If my sample's garbage and it's not representative, is my confidence interval any good? No. Confidence interval is only as good, our statistics are only as good as my sample and my methods, right? But assuming that I've got a decent sample, these should be valid or reasonable estimates, okay? We've got data collected in the study suggests average scores in the 1980 exam falling below 104.2 or above 109.8, not compatible with estimates of performance in this in the current population, right? So Allie might say, well, I think the average score on this 1980 test today is 115. Like, well, maybe. I don't know. Based on the data that I have, though, that doesn't seem like it's reasonable, right? And then maybe Eric is like really hard up on this 1980s test. She's big on it. It's her favorite, right? She's like, no, I think it's still valid. I think the average really is 100. You just asked a bunch of smart kids. Like, maybe, I don't know. But really, if I'm assuming I've got a good sample. Now, if I went through and I sampled just graduate students, would that be a good estimate of the current population? No. But assuming I got a decent sample of just sort of the general public, 100 is probably not reasonable, right? You say results suggest an average score of 107 on the 1980s exam in the current population of adults, with estimates indicating expected error of estimation plus or minus 2.8. Estimates of performance on the 1980 exam compatible with these data range from 104 to 104.2 to 109.8. Right. So again, the thing that I'm hoping you take from this is we're sort of saying sort of these are things that are compatible with the data. Now, my data, Natalie, do I know if my data are any good or not, or whether or not that this confidence interval that I've got actually captures the true population parameter?
I don't think you know for sure.
I don't know for sure, right? Again, if we go back through, right, my interval is just one of an infinite number of intervals that could be collected, right? And it's possible that this is my interval, or that this is my interval. I don't know, right? If I've done a good job, I don't think it's likely, but it's possible, right? So it's possible that my interval is way off base, but at least based on the data that I've collected, this to this seem like reasonable guesses for what this parameter is that we're looking for, right? But again, this is why it's always so important to place your findings within the context of larger research, wanting to go through, see what other people have found. This is why meta-analysis is so important, because if everybody else who's ever looked at something finds that values tend up ranging from here to here, and I do the exact same thing and find something way off over here, that might be cool, and it might increase with my likelihood of getting something published because it seems weird that no one has ever found. But should I be super confident that my data are representative of what anybody else is going to find? Probably not. I might not have even done anything bad. I might have done everything perfect, right? It's just that sometimes this is going to be our study, okay? And this is where the replication crises come into play, right? Again, if people understand sort of how this whole system works, you shouldn't be shocked. It's almost certainly going to happen, right? But every once in a while, if I keep trying to replicate the same study over and over and over again, eventually I'm going to get something that's out here, right? And if I ignore the fact that I tried to replicate it 10 times and it all failed and I've only got one thing that turned up, I should be very suspicious about that one time, right? Question, who do I want to pick on here? Brittany. If we're looking at this, sort of say, let's pretend that this is replications of intervals, right? When would I expect more spread across these intervals if I'm working with replication of a very large sample or a very small sample?
So you're asking me, like, if you like replicate a study, are you looking for more like spread across a small sample or a large sample? Like,
Yeah.
I would say small, right?
Yeah, exactly, right? If I'm running samples of 10 and 15, these individual intervals are going to be all over the place, right? Because they're much less stable. If I'm running a sample of 500, right, I'm going to get some variation, and it's possible every once in a while I might get something that falls out, but in general, everything's going to be pretty stable, right? So we want to be thinking about evaluating all of our research and all this stuff in terms of level of precision and sort of likely replicability. We never know based on one study, but these are things that we want to be thinking about, okay? So here, in terms of general conclusions, once again, our average performance on the old test and the current population pretty precise, given that we've got a margin of error about 2.8 points, again, assuming that we've got decent sample. And again, we would say results are consistent, look to be consistent with expected effects of the Flynn effect, in that Allie is 100 So again, sort of this test in 1980 was normed at 100. Is 100 a reasonable estimate for this true score in the population based on the data that we've collected?
Not really.
No, no. It's not impossible, but it's not plausible, right? So now what we would need to do is we would say, okay, we've got if I'm thinking about performance on IQ scores, is a difference or a deviation of 4.2 points meaningful, right? So we're talking about, well, it's shifted from 100 to 104.2. Knowing sort of just because Tara does this stuff, I would say probably for the field that's a notable increase. But this is the other thing we always want to do is ask ourselves, okay, so it looks like sort of our hypothesized value it's not in there, but is the deviation, again, minimum deviation, is that enough to get excited about? Wanted to think about that a little bit. Okay. Questions about how we're going through and using our interval estimates here? Okay, cool. So again, we went through this at the end of class last time. Remember that our point estimate is always our best guess. Okay, Erica, you found a confidence interval, and you find that in this example, you're getting an average score of 107, but your 99% interval says anything between 104.2 109.8, reasonable given the data that you found at a 99% confidence level. But still, what's your best guess for the average performance score on this 1980 test in the current population? 107, right? So again, and this is where I think people get a little bit screwed up. They think, oh, anything in this bounds are equally likely, and then everything outside of those bounds are impossible. It's all running on a distribution. Okay. So again, same thing with my IQ scores. 107 is still my best guess. Do I think it's exactly 107? No, I know it's not, right? Hopefully I'm close. It should be in there, but anything from 104-ish to 109-ish is probably going to be reasonable. But even as I start to get out there, it's not impossible, right? It's just not likely given the data that I've collected. All right. What we can do then is we can start to add in multiple samples and start to get a little more elaborate with stuff. So in this example, so we've got a certain chemical has been hypothesized to improve memory. We've got a sample of 10 newborn rats given a normal diet containing lecithin, 7 rats in a separate sample given a diet with no lecithin. When all the rats reach adulthood, we give them a rat memory test, whatever that looks like. Lecithin sample, okay, so the rats that got sort of the memory boosting stuff have a mean of 25, variance is 61. No lecithin sample, data mean is 33, the variance is 36.5. We're assuming that performance on memory is assumed to have a normal distribution based on this strain of rat. And what we're saying is we're saying that in these data, because I do rat memory, this is my jam, right? And so what I know is that scores that deviate by more than 7 or more points are going to be interpreted as having high practical significance. Okay, so we're starting to add in a little bit. So we've got a couple of different groups. And what we're going to do is we're going to calculate the point estimate for each group, calculate confidence interval group for each group, and then try and sort of do some interpretations around this. Okay. So, Erica, one more, and just because you're in the middle of my screen right here, what are my point estimates for the average the average performance in the population of rats that get no lecithin, or the rats that do have lecithin?
The ones that don't get lecithin is 25.
Uh-huh.
And the one that does get the lecithin is 33.
Okay. So switch that around. So it's a little bit tricky, right? So our lecithin sample, 25. Our no lecithin has 33. Okay. Is that surprising anybody? Or is anybody sort of based on the setup of the question, anybody seeing anything that's raising bells with this? Yeah, Brittany, say something about that. Yeah, what are we talking about here?
So you'd assume that the lecithin rats would have better memory, but the point estimate shows you that right now the no lecithin, that's a hard word to say,
Yeah,
sample has right now has better memory compared to, which is 33 compared to the ones who do have it at 25.
exactly. I'm giving you a giant virtual hug right now. Okay.
Thank you, I need it.
Yeah. Okay. Always, always, always remember that when we're doing this stuff, we want to go through and not just say, oh, there's a difference or there's not a difference. We're hypothesizing a difference in a specific direction, right? We're saying that this lecithin compound should improve memory. I've got an experimental group where I've deprived of lecithin, but my sample there, I don't know if it's meaningful or not, but the no lecithin group is performing higher on memory than the one who got the normal diet, which is not what I was expecting, right? So already things should be sort of triggering like, okay, what's going on with this? Okay. So if we go through and we have our control group, mean, variance, lecithin group, sample size, mean, variance, go through point estimate for my control is 25. My no lecithin group is 33. Already things are backwards than what I'd expected. Going through and calculate my standard error. Here, because I've got variance, I can also just take my variance over my sample and take the square root of that. It's mathematically equivalent to first converting to a standard deviation. Do whatever you want. Just make sure that you're doing it right. So we get a standard error for my control group. Do the same thing for my no lecithin group. Get my standard error. Confidence interval for my controls. So these are folks who should be doing better. Confidence interval for my no lecithin, experimental no lecithin group. And again, Brittany, sort of building on what you had noticed earlier, what are we seeing with this?
Oh god, I don't want to read what you said. I'm trying to like do it myself, basically, because it's right there. So the control group that did receive lecithin, their memory varies with a 95% confidence interval between, I don't know if this is right, you can correct me, 20.16 and 29.84.
Uh-huh.
Is that okay?
Yeah, no, that's good. And what about the no lecithin group?
The no lecithin group with a 95% confidence interval have their memory varied between 28.53 and 37.47.
Okay. So at most, sort of based on our data, what's the highest value supported by our data for the average memory score in rats with a normal lecithin diet?
What? 37.47?
No, with this is our control group.
Oh, is that the one you're asking about?
Yeah.
Oh, the 29.84, right?
Okay, so our rats that had lecithin in their diet, like at most, our data supports an average memory score of about 30, right?
Oh, okay.
What's the minimum supported value for memory in our rats that don't have any lecithin?
It's the same one, right? Am I not?
Okay, so the control is the control is the group that has lecithin in the diet.
Oh, okay. So didn't have lecithin. I would just say 29.
28 and a half, right? So what we're seeing based on this is we thought it was going to go the opposite direction, right? But based on my interval estimate, the upper max supported the value of memory from the data for my sort of rats that should be doing better is just a little bit over the minimum estimate for my rats that had no lecithin that shouldn't be doing worse, right? So we've already got some problems here. So if we're going to go through and create examples, we say population estimates for the average memory score of rats receiving standard levels of dietary lecithin, 20.2 to 29.8, with point estimate of 25. Point estimate in rats with no dietary lecithin, 33, with population ranging from 28.5 to 37.5. Okay, so quick with this example, Rachel, what are my populations that I'm referring to here, or what are my target populations?
receiving the standard diet
Uh-huh.
and rats who don't receive the standard diet.
Yeah, right. And so is this a real population or is this a hypothetical population?
I think it's a hypothetical population. Well,
Yeah,
it's one.
yeah, no, perfect. Yeah, which one's the kind of hypothetical population?
The one where you're taking away the
Yeah.
whatever that is.
The lecithin, yeah. And this is an important thing to remember, right? So the natural sort of rats just getting normal diet, that's just rats getting normal diet, right? So that's an easy sort of a real life population out there. But the population of rats that may have had lecithin like restricted and never had it in their lives might be the 7 rats in our study, actually, right? We're not interested in the 7 rats in our study. We're interested in this hypothetical population of if we were to deprive all rats of lecithin, what would be their average memory score, right? This starts to become important when we're thinking about our studies that we do, like experimental studies and things like that, right? Let's say Ari has a study where she's doing some sort of experimental manipulation, looking on spatial reasoning or something like that, right? And it's some sort of lab-based paradigm where she's got someone's doing something in a VR machine or something like that, right? Now, what's the actual population of people who have done that? It's going to be the people in Ari's study, right? But the idea is that were we to do this to everybody in the world, this is about what their score would be, right? So when we're thinking, we're just wanting to be thinking carefully about who's our sample, who's our population, and recognizing that from some of our experimental work, our samples may be hypothetical, or our populations may be hypothetical populations. Same thing. Let's say Natalie's doing work on sexual assault prevention, right? And you've got, say, 20 students that you have going through some sort of program or something like that. And you measure the average level of rape myth acceptance for those individuals. Now, who's the population? Well, those are the only people who've gotten it. So that technically is the population. But the idea with our study is if we were to deliver this to all undergraduates at all university, or let's say all graduates and undergraduates at the University of Wyoming, we're expecting that sample to represent about where the rape myth acceptance would be if everybody were to have gotten it, right? So just being careful in terms of how we're thinking about things. So general conclusions, precision of these estimates is poor given the width of our confidence intervals. And again, this is because we've got small samples. Before we're working with samples of 120, 150. Here, we've got memory scores ranging anywhere from 20 to 30, 28 to 37, right? We've got really big intervals with this. We've got not many people. Our samples aren't super precise, right? Or our estimates aren't super precise, so we want to be thinking about this. So although we've got our point estimates for memory scores outside the confidence bands of opposing groups, we've got some degree of overlap here, right? So for this, my control group, Riley, is a score of 33 within that confidence bound here?
No.
No. And is a score 25 in this confidence bound? No. But there's still some overlap here, right? And so we would say results are compatible with differences in the population estimate, ranging from 1.3 points higher in the memory for lecithin restricted rats to 17.3 points higher for rats with normal dietary stuff. Okay, Riley, where am I getting that from? The 1.3 to the 17.3.
There's some subtraction going on.
Yeah, there is some subtraction going on. So let's say, based on these intervals, right, my data would really support differences in these data ranging anywhere from, let's say, my control has an upper limit of 29 compared to my lower limit of 28 for my no lecithin group. If I subtract that, this gives about a little over a point advantage to the normal control group, right? On the other hand, if I see if my control group actually has a value of 20 and my lecithin group actually has a value of 37, we've got a swing from about a 1 point benefit for the lecithin restricted or for the control rats all the way for a 17 point swing for our other rats. Okay, and so our data here support the possibility of no difference, right? As well as the possibility of huge differences, right? And differences going in the opposite direction, right? So really my confidence intervals say, I don't know, results could be sort of a little over a point higher in this group to about 70 points higher in this group. And everything's turned around backwards. 0 is a possibility. There might be no difference at all, right? And so basically what we can say based on these data is we need a lot more data to go through and take a look at this, right? The fact that it's turned in the opposite direction is really strange. And I would want to go through and see whether or not other studies have gone through and done this type of thing. I want to go through and take a look at my close methods. Anytime I get something that's the exact opposite of something that everybody else has found, I want to take a look at my study and see if I've done something weird or if I've made a mistake or if something in my methods has sort of turned things all the way around. But basically with this data, we would probably say I can't come up with strong conclusions based on these data because I have anywhere from a small benefit in this group to a massive benefit to this group or no difference at all. We just don't know, right? And Allie, what is contributing to the inconclusiveness of these data?
I mean, the small sample size.
Yeah, it's really the small sample size, right? And this is the problem we have with our small samples. The level of imprecision is huge, right? We say, I don't know, here's my best guess, but it could be anything from here to here, right? And because of that, it's hard to say. Again, sort of just using intervention stuff because it's easy to say my treatment for depression my point estimate is it gives me a 15-point reduction in scores, but that could be anywhere from a 3-point increase to a 40-point decrease. So who knows, right? Any value in that based on my confidence interval, any value in there is supported by the data. So I really can't say much about it. Okay. So I think one of the things that we want to do with our statistics is we want to get very confident to say, oh, this is what's going on, or this is what's happening, or this is clear evidence of an effect. And sometimes our studies can show us that. But I think one of the reasons people don't like to use confidence intervals is it sort of really illustrates that we often know a lot less than we would like out of our studies, right? And if we're looking carefully at the precision of our estimate, we're saying, I don't know. So my study looks pretty good because I found an effect, but my data supports anything from a trivially small near zero effect to something that's massive. Anything in the middle of that could be supported. So I don't know, right? Definitely want to go through and start thinking about sort of replication and sort of further evaluation. Okay. People comfortable. So does this help people kind of get an idea for how we start to use confidence intervals and sort of just the information that we can start to pull and glean from this? Okay, cool. Some guidelines for comparing confidence intervals. Again, you've got a really, really excellent paper assigned that start to go through this Cumming and Fitch paper starts to talk about this. Make sure to go through and read that carefully. First thing we always want to do in any type of graph is identify what our error bars mean. Are they standard errors? Are they confidence intervals? Make sure that you're clear on that. Make sure that we know what the means are. Make sure that we have a good interpretation of our confidence bounds. And then for independent means, if we're doing independent sample tests, Cumming and Fitch talk about if our margin of error, if the overlap in our margin of error is no greater than about 50%, if we were to run a hypothesis test or an inference test with this, our p-value is going to should be close to less than 0.05, right? If our margin of error if there's no overlap in the margin of error, we would expect a p-value of less than 0.01. And again, our margin of error is the difference between sort of mean to upper limit, mean to lower limit. Basically, if we've got no more than a 50% overlap here, assuming we've got reasonably equal sample sizes and samples that are sort of reasonably sized, we can start to infer things about overlap in these intervals. This is super helpful because oftentimes you'll be reading papers and people won't provide tests that you want, but if they provide means and confidence intervals and things like that, you can start to sort of glean information there. Okay. All right. Questions on any of that? Okay, cool. Let's go through. Let's take a 10-minute break. Jump back at 3:50, and we'll jump into our next set of slides. All right. Thanks, folks. We'll see you in a bit. Cool. All right, cool. Questions on confidence intervals. Are we feeling comfortable with sort of this idea of interval estimation, how we can use it and start to sort of kind of pick out some important pieces of information that go above and beyond just saying something's different than 0? Comfortable with this? Yeah, go for it, Riley.
I have a question on how to interpret them.
Mm-hmm.
So I was just thinking about it, and if I were to say, so at a 95% confidence interval, if I were to replicate the study 100 times, is it correct to say that 95% of those times would, I wrote it down, would report an interval that captures the estimated population parameter? Is that correct?
Yep, you're exactly right. That's perfect. And that's the technical definition of an interval estimate, right? The interval estimation is about the process, right? And it's not about any specific interval. And this is why it's incorrect to say that there's a 95% chance that this interval between 90 and 110 captures the true population parameter, right? Because whether or not this specific interval, contains the true population parameter, either it does or it doesn't. Yeah, it's not a percentage thing, right? It's either there, it's not. But if we were to repeat this study over and over again with samples with replications, we would expect 95% of the intervals that could be created to capture sort of our population parameter of interest. Now, the reason I don't want you to use that, you're exactly right. Just don't use that in your actual interpretations unless I ask you for the technical definition, because 1, it's bulky, and 2, the average person doesn't think about things in terms of infinite number of replications, okay? And so this is why we start saying, based on these data, or assuming the model, so data-supported estimates for the population parameter range from this to this, or sort of this to this, based on the data we've collected, would be considered plausible values for whatever it is that we're looking for, right? And so not even getting into, people say, oh, well, how do I get into the confidence level? No one cares about, you shouldn't care about the confidence interval. You need to report it to say, I'm reporting 95% confidence intervals or 90% confidence intervals or things along those lines. But don't worry about trying to work that into your estimation, because what ends up happening is you drift into talking about there's a 95% chance of something, right? You can say, based on a 95% confidence interval from these data, we would expect reasonable estimates of whatever it is we're looking for to range from this to this, or we've got a point estimate of this based on a 95% confidence interval. Expected margin of error in the estimation is plus or minus 5 points on that, right? So these are the types of things that you can start to go through and use flexibly in a way that makes sense, as opposed to cutting and pasting and using the same stock phrase over and over again, because that's repetitious and it doesn't actually sort of demonstrate that you're using that flexibly, and it'll get really boring as you're going through and writing, and it'll make you seem redundant, like I'm just making you write your name on the board over and over again, when that's not the point. I want to get you to get comfortable using these in a way that starts to provide a considerable more nuance in terms of interpretations. Does that help, Riley?
Yeah, it does.
Cool. Any other questions about how we're using confidence intervals, approaching that in terms of our data? Cool. All right. So let's pop into next set. Talk about some distribution of sample means, some hypothesis testing stuff, some very preliminary z-score things. All right, so quick overview. Going to talk about distribution of sample means, some central limit theorem, talk about null hypothesis significance testing, kind of the parameters of what we're doing here, but then get into some of the criticisms with this, and then recommendations moving forward. So up to this point, everything that we've done has really focused on identifying the location and probabilities of values within a certain population of scores. So I've got a population of scores. What's the likelihood of identifying a value of this or higher, or that or lower? So to some of our z-score stuff that we're doing, right? I've got a population with a mean of 100, standard deviation of 15. I have this specific score has a z-score of 1.96. What's the probability of identifying a score at this level or higher, or at this level or lower, that type of thing, okay? But the issue is, when we're doing applied research, it's very rare that we're interested in sort of the probability of an individual score, okay? The score, again, our samples are ways of going about and inferring something about a larger population. And so what we generally are wanting to do is, more often with actual research, wanting to make some sort of inference based on means taken from a sample of scores. So instead of saying, what's the likelihood of someone scoring at or above Brittany or at or below Natalie, we want to say, what's the likelihood of obtaining a sample with a mean of what's the probability of obtaining a random sample having these types of characteristics, okay? And this is what really gets at the heart of our inference tests. And so just like we can go through, and if we know what a distribution looks like, if we know the properties of a distribution, we can go through and start to assign probabilities or likelihoods of randomly obtaining a score of a certain value. We can do the same thing, use the same process to start to look at and identify the probability of obtaining a certain sample of a certain size with certain characteristics relative to some assumed distribution of whatever it is that we're looking at. So we're taking the same thing that we did with the z-scores with the individual scores and applying this to samples and studies and things along these lines. Okay, so the way we do this, and a fundamental sort of principle in terms of understanding what's actually going on behind our statistics, is understanding this idea of our distribution of sample means. Okay, distribution of sample means is the distribution of means of all possible random samples of a particular size that could be drawn from a population. Okay. Before, what we're talking about distributions of individual scores. With our individual distribution of sample means, what we're looking at, sort of the observations in our distribution, are means of samples. Okay. So, for example, if I, again, let's just for convenience sake say my population of interest is University of Wyoming students, okay? We're saying on-campus students, okay? And we're interested in the average height of University of Wyoming students for whatever reason. We've got boring research agenda. But let's say that I go through and I grab a sample of 100 randomly recruit a random sample of 100 undergraduates and measure their height. Okay, and Rachel, what's my mean value that I get with my average, or what's the average height for my sample of 100 students?
Oh, do I just make it up?
Yeah, just make it up.
Okay. 5'8".
5'8". Okay, so then I go through and I get another random sample of 100 students. Rachel, what's my average height for that sample?
5.7.
5.7. And if I were to ask you that same question, for all possible samples of 100 students with replication, you would give me a range of answers, right? But what we would assume is if we went through and calculated the average height of all possible samples of 100 that could be drawn from the population of UW undergraduates, what we would have is a distribution of sample means, okay? And so in practice, right, again, functionally countless number of samples with replication of size 100 could be drawn from UW undergraduates, right? It's not necessarily countless, but it's going to be a very, very large number, okay? And it would be impossible to go through and do this all directly, right? So again, this distribution of sample means is kind of a theoretical sort of entity process, like a lot of the stuff that we're doing, okay? But luckily, what we've got is certain equations and certain sort of the people smarter than me, the statisticians have gone through, mathematicians have gone through and worked this all out, so we don't have to go through and draw all samples, random samples of size 100 with replication from the population of university undergraduate students to know what the properties of that sampling distribution are going to look like. Okay? So we're going to do just a really oversimplified demonstration, but I think it sort of illustrates this. Let's say we've got a population of 4 scores, okay? 2, 4, 6, and 8, okay? And this is my population. These are the only 4 scores in the universe that represent sort of this sort of group, okay? There's only 4 of them, okay? And if I go through and I plot this out in a histogram, I've got 2, 4, 6, 8. I've got a mean value of 5, okay? Allie, how would we describe this, the shape of this distribution?
The shape of it?
Yeah.
It's just like,
Yeah.
I mean, everything's the same.
Yep, it's flat. It's a uniform, it's a square distribution, right? We have one value at each one of these scores, so it's not much of a distribution at all, right? It's just a flat, it's a square distribution, right? Is it normal?
No.
No, not at all, right? But this is the population that we're working with, okay? So what we could do, though, so we've only got 4 scores, but from this population of 4 scores, what we could do is we could construct a distribution of sample means of sample size 2. So if I were to go through and randomly grab samples of size 2 from this set of 16 scores, or excuse me, of this set of 4 scores, and again with replication, right? There are a total of 16 unique samples that could be drawn from this, okay? So my sample 1, my first draw, I get the person with a score of 2. So to throw them back, because it's with replication, I get them again. So there we get that. So we've got 1 sample. Next sample, get the person with with a score of 2, throw them back, get someone of 4, so on and so on and so on. With only 4 scores in my population, there's only 16 unique samples that I can draw. Okay, so if I go through, here's my first score, here's my second score, and what I can do is then compute the mean of all possible samples of size 2. So here, my mean is 2, 3, 4, so all the way up to 8. Okay, people see what I've done here. Okay, and so what we've done in a very, very small way is we've created the sampling distribution for this population of 4 scores of sample size 2. And this is all the possible scores that we can get. We've gone through, we've drawn all our samples, we've calculated a mean, and then what we can do is we can plot those out, okay? And what we have is a distribution of sample means for all samples of size 2 from this set of 4 scores. Allie, I'm going to go back to you. What do we notice about the distribution of sample means?
It's more normal, or like it's kind of like a normal curve.
Yeah, right. It's a much different shape than my original population of scores, right? My original population of scores, pretty square, right? My sampling distribution now looks much different and is looking much, much more normal, okay? And so what we see, and this is sort of a fundamental feature of sampling distributions, we see our sample means start to pile up around the population mean, okay? And what we see, Allie, what just based on eyeballing this distribution here, what's the mean of my distribution of sample means?
Probably 5.
Yeah, it's 5. What's the mean of my population of scores? Over here.
Oh,
5. Okay, this isn't an accident. What we see is the mean of the sampling the mean of our sampling distribution, or the mean of our sample means, is going to pile up around the population mean, so that the mean of my sampling distribution is mathematically equivalent to my population mean. Okay, we'll see that the distribution of sample means will generally form a normal distribution. Asterisks under certain circumstances. There's situations where it won't, but it generally will if we're doing sort of a reasonable job with our methods. And what we can do is we can use the distribution of sample means, or the assumed features of our distribution of sample means, to start to answer questions about the probability of selecting a random sample having a specific mean. Okay, so if I go through and I take a look at this, Allie, so one more time and then I'll leave you alone for a bit. What's the probability of randomly selecting a sample with a mean greater than 7?
It's going to be 1 out of however many are in here. Sorry, 1 second.
Yeah. 1 out of how many?
16.
1 out of 16. Okay. So with this, right? With this here, I can say, if you ask me what's the probability, if I've got a population of 4 scores, right? What's the probability of randomly selecting a sample of n equals 2 that has a mean greater than 7? I can say 1/16, right? It's just this gal here, right? Or we could say about 6.3%, right? And so what I can start to do, if I say my hypothesis is that that the mean of my population is 5, and I go through and I run it, and I get a sample of 2, and I get the mean of my sample of 2 is 7, or excuse me, 8. Is that a likely occurrence or an unlikely occurrence? What do you think, Riley? We'll leave Allie alone for a minute.
Sure, I think she's like dying to answer. Sorry, can you repeat the question?
Yeah. So if I say I think my target population has a mean value of 5, and I go through and I collect a sample of 2 and get a mean value of 8 in that sample, is that a likely sample or an unlikely sample?
Unlikely?
Yeah, it's unlikely, right? And so what I can start to do is start to make certain inferences about the likelihood of my estimated population parameter and things along those lines based on sort of assumed characteristics of my distribution of sample means. So the shape and properties of our distribution of sample means determined by central limit theorem here, okay? And we can use mathematical theory, sort of stuff that we won't worry about. I'm not going to have you derive anything, right? But what we know is sort of based on statistical theory that for any population that has a mean of mu, standard deviation, sigma, distribution of sample means of sample size n is going to have a mean of sort of equal to the population mean, standard deviation equal to standard deviation equal to population standard deviation, but divided by our sample square root of our sample size, and it's going to start to approach a normal distribution as our sample size approaches infinity. Okay, this is a central limit theorem. There's a lot of sort of stuff going on in here, but what this means, okay, is that we will see for any population, right? The distribution of sample means is going to start to approach normal under two different conditions. One, if the population from which we're drawing scores or samples from is normal, okay? So, Brittany, if we're assuming that height has a normal distribution, okay? If I start selecting random samples of people, let's expand it from the University of Wyoming to the U.S. population. If I'm assuming height in the U.S. population has a normal distribution, if I start going through and collecting random samples of any given size, my distribution of sample means is probably going to be very quickly approach normality. Okay. Now, what happens if I'm looking at, does anybody study anything that's pretty rare or not common?
What do you mean by that?
I don't know. There's something that doesn't happen a whole lot.
Suicide?
Okay, so yeah. So Rachel, so if I'm looking at rates of, or let's say suicide attempts, so that people are sort of still around, right? If I looked at the distribution of suicide attempts in the U.S. population, would that be a normal distribution?
I don't think so.
No, probably is not going to be, right? We're going to have a skew, right? We're going to have most people have zero, but then sort of people with increasing difficulties having more and more attempts, right? And so what happens then? Well, turns out that if we're looking at suicide attempts, sampling distribution is still going to start to achieve normality as long as our samples are about 30 or larger, okay? So even if whatever we're looking at in the population, whatever it is, still has a really, really sort of non-normal distribution, doesn't matter. As long as we've got reasonably sized samples, and again, 30 is not a huge sample, it's a pretty small threshold. But if we start to get at least reasonably sized samples, we know that the distribution of sample means is still going to approach normality very quickly, okay? So that we know under conditions in which whatever we're looking at in the population has a normal distribution, or even if the population distribution isn't normal, as long as we're collecting sample sizes about 30 or more, that distribution of sample means is still going to start to approach normality and sort of pretty quickly with this. Okay. Questions about this? Okay, so this is a known characteristic of the shape of sampling distributions. Okay. We also know something about the central tendency of our distribution of sample means. We know that the mean of a distribution of sample means, or in other words, the average of all possible sample means of a certain size is going to equal the population mean. Okay, so here, Erica, let's say that we've got random samples of adult height from people in the U.S. population, and that we know that the population average height of the U.S. population is 68 inches. Okay? If I go through and I collect all possible samples of size 100 from the U.S. population, and I were to plot the means of all those samples out, I would get my distribution of sample means. Okay, and what I would find is that the mean of my distribution of sample means is going to be 68 inches. Okay, and what we call this, we refer to this as to our expected value of the mean. Expected value of the mean is the mean of the distribution of sample means, and it's going to be equal to our population mean. Okay.
Good question.
Yeah.
So sample means, just to make sure I'm understanding this right, sample means, that term means like you have multiple samples, all those means.
Yeah, exactly.
I just want to be
Yep. No, this is perfect. Because in this graph, right, this is just a histogram of all possible means of size 100 that could be pulled from the population. Okay. Now, are all of those means going to be 68 inches? No. I'm going to get some samples that are higher, some samples that are lower. I'm going to get sort of in the very, very rare case, some that are super high, and in very, very rare cases, some that are super small. But in general, the distribution of sample means, again, all samples that I could pull from with replicate or with replacement from size 100, this is what the distribution of those means would look like. Okay. And so I know that very quickly that's going to approach normality. And I know that the mean of the distribution of sample means, or my expected value of mean, is going to be equal to my population mean. All right, so this is central tendency. Last thing we want to talk about is the variability of this distribution of sample means. Okay, we can calculate the standard error of the mean. Okay, and we calculate this as my population standard deviation divided by the size of whatever samples that I'm running. Standard error is going to be the standard deviation of the distribution of sample means. Okay, so Ali, you had said before when we were talking about standard error, I had described standard error as the extent to which I expect on average a replication sample of a given size to start jumping around relative to my sample, relative to the mean, things along those lines. And you had said, well, it kind of sounds like your standard error is kind of like a standard deviation. You're exactly right. Standard error is just the standard deviation of my sampling distribution. And we can think about this in a couple of different ways. We can think about our standard error as an index of how much difference to expect from one sample to the next, right? So if I've got a really big sample, Robert, I got a really big sample, and I've measured a mean in my really big sample. How much do I expect if I were to, and let's say it's sample size 250. So I go through and get another random sample of 250. How much do I expect my point estimate to jump around across replications of 250? A lot or a little?
Not much.
Not much, right? What if I have sample size 15? Do I expect those to jump around quite a bit? Yeah. So we can think about our standard error as the extent to which I would expect means to start jumping around, right? The bigger the sample, the more representative and the more stable my estimate. I'm going to expect less movement. As I start to get into small sample stuff, things are going to jump around a great deal, okay? So we can think about standard error as the how much we expect individual replications to jump around. We can also think about our standard error as how well any individual sample represents the population mean, okay? So in this case, if we're talking about random samples of adult height, if I were to be able to get random sample of 20 people from the U.S. and measure their height, should I expect that to be a very precise estimate of the population parameter? Nope, right? What if I had a sample size of 10,000? Yeah. Right? And so we can start to think about standard error as a measure of how well I should expect my sample to estimate the population value that I'm interested in, okay? We can also think about standard error as the expected difference between a sample mean and the population mean, okay? On average, and this gets back to Ali's observation that this sounds kind of like a standard deviation. Yep. We can use this standard error as an indicator of if I were to randomly sort of pull a random sample of size whatever, about how far would I expect this sample to deviate from the true population parameter, which in essence is telling me sort of, again, an indicator of how good my estimation is here, right? And so any of these ways are all sort of equally valid ways to go through, and Riley's in the middle of a fight.
I'm not safe.
You just got scratched. Is that your cat or someone else's cat?
It's mine, but God, you wouldn't think so when she attacks me.
Yeah, I don't know. Mine's not up here. He likes to jump around and mostly just put his tail in my face, which I don't understand, but all right. So any of these ways, and again, I can't emphasize enough how important it is to understand on a conceptual level what we're talking about in terms of standard error. It's just giving an estimate of precision, okay? Bigger samples give us better precision, give us smaller standard errors. And so again, thinking about standard error as the standard deviation of our distribution of sample means. Up here at this link, I know, brace yourselves. What I've done is I've created a YouTube video that goes through an applied demonstration of standard errors with actual data and graphs and stuff like that. I know. Oscar hasn't called yet. They'll be here soon, I'm certain. But if you go through and just want to get a good sort of a visual of what's going on here, would definitely encourage you to go through and take a look at that. What we're doing is going through and I'm using different data, randomly generated data, to show that with replication, kind of what happens with these sampling distributions. Okay. Questions about distribution of sample means, shape, central tendency, characteristics, anything along those lines. Okay, so things that impact our standard error. One, population standard deviation. As whatever I'm measuring, if whatever I'm measuring has more variability, right? People tend to be more different versus something else where people tend to be more same. Population standard error deviation will impact it. As a standard population standard deviation decreases, standard error will decrease. Okay, but that's trivial relative to your sample size. Okay, our law of large numbers say the larger the sample, more likely that sample is going to be closer to the population mean. I'm just getting a bigger segment of the target population. It's going to give me a much more precise and much more accurate estimate of whatever it is that I'm trying to get. Okay, and if we go down through, remember that our formula for standard error is just a standard deviation divided by the square root of our sample size. I plot this out like a cool kid. What you see as my holding this value equal, right? As my sample size starts to increase, we see a dramatic reduction, and then things start to kind of level off here. All right. Now you'll hear some people start to say, sample size of size 30 or sort of greater is a large sample. Samples of 30 are not large samples. But from a statistical standpoint, Robert, what starts to happen at about sample size 30?
It's when your sampling distribution starts to become normal.
Okay, that's true. That does happen. Good point. Looking at this graph, what happens at about sample size 30 relative to your standard error? What's that?
Or the graph starts to plateau off.
Yeah, okay. What we start to see is sort of in very, very small samples, as we start to increase our sample size, we get dramatic reductions in our standard error. We'll hit a point where things start to level off, right? And so in statistical literature, when you'll hear particularly old school stuff, people say, well, sample size of 30 is sort of considered a large sample. You see this in textbooks. It's not. Trust me, it's not. You should never try and claim that a sample size of 30 is large, unless you're looking at really, really rare people who are terribly hard to get, and then maybe. But from a statistical standpoint, all this means is that the impact of additional people on our standard error starts to plateau out, right? Now, as our sample size continues to get larger and larger and larger, our standard error will continue to go down and down and down, but sort of you get diminishing gains sort of as your sample size gets larger and larger here, okay? But again, this is where don't ever ignore sort of these formula, because you can just look at that formula and just immediately tell exactly what the influences are, what the effect's going to be. It's a nice way to just go through and tell stuff. Okay. So this is just a demonstration. So here's a distribution of sample means for different size sample. Erica, which one of these graphs represents would be the sampling distribution for our smallest sample size?
Maybe the blue one.
Here. So the blue one, but then look. Okay, let's say this black line is your distribution of actual scores. Okay, and so which one of these samples, the red, green, or blue, is going to be what I would expect the distribution of sample means to look like for my smallest sample.
The red, because it's more spread out.
There you go, right? Because if I've got a smaller sample, what am I relative to a larger sample? What do I expect my standard error to be? Bigger, right? And here, if we think about your standard error as as the standard deviation of your distribution of sample means, we see that this red this red distribution here more variable than the green or the blue. Okay, and so Eric, again, so which one of these would represent the sampling distribution for the largest sample? The blue, yeah. It's much less variable, right? So we would expect less jumping around from sample to sample here. Okay.
Can I ask you a question? I'm sorry.
Yeah, no.
I just wanted to make sure. So the reason that the blue has less variability is because it's like, I don't know a better way to say this. It's like tighter to the mean. What we know is the mean.
Yep, exactly. Yep. So, for example, Brittany, let's say if we say this is a value of, I don't know, let's say this is 1, let's say right here where my pointer is a value of 110. Is that a rare score for the red distribution?
No, because it's more variable, right?
Yeah. Is it a rare score for my blue distribution?
Yeah, because it doesn't even,
right.
I mean, it's towards the bottom, like the table says.
Exactly, right? And so this is the thing, right? When we have low score or when we have smaller samples, we have a huge standard error. And so we expect lots of variability, right? So if I have, so I'm about 6'3", okay? Let's say, is that a more rare score for a sample for measuring people's height? Would that be a more unlikely score if that was the average of the sample, if I have a sample of 15 or a sample of 200?
So, if you have a sample of 200, it's more likely to have someone who's 6'3", right? Is that what you're asking?
Yeah, it's more likely to contain somebody who was 6'3", but let's say, hey, I grabbed a random sample of people and the average height was 6'3". Is that more likely to happen in a sample of 200 or a sample of 15?
Probably 15, right?
Yeah, right.
Okay.
Now, it's not likely any time unless I just happen to randomly grab a bunch of tall people, right?
Yeah.
But it's a much, much, much rare thing, particularly if we say average height is, say, 5'10",
Yeah.
in a more variable distribution than a less variable distribution. Okay. Excellent question. Other questions? Okay. So what we've got here is basically 3 different distributions. We've got our distribution of population scores. Okay, this is all scores in a population. Population scores have its own shape, mean, variability. This is all the individuals, units in the world that compose this population. This is a hypothetical thing. We can never, or rarely, if ever, actually have access to the full population, right? This is something that we think about kind of on a theoretical out there in the universe. But that hypothetical population, or that thing that we'll never ever to observe directly, has its own shape, has its own mean, has its own level of variability. Okay, but we can't get that population of scores. So what we do is we get our sample of scores, and we hope that that sample is representative. We hope that sample is sort of random and sort of captures all the sort of different characteristics of the population of interest. This sample is a subset of scores that we're hoping represents the population, but it again is going to have its own shape, mean, and variability, right? That's going to be different in some ways from the population. Okay, someone. For 1,000 points, tell me what do we call the difference between a sample statistic and a population parameter?
Sampling error?
Yes, sampling error. Robert gets how many points? I said 1 billion points, right? I think that's what I
I
said.
think you said whatever's in A.
right? That's what, you know what, you chose door number 2 and your PhD is behind there. You just finish it up. We'll just send you on your way right now, right? Okay, yeah. It's just my sampling error, right? And so my sampling distribution is my distribution of sample scores is going to have its own distribution, shape, mean, variability. And then I'm going to have a distribution of sample means. Distribution of sample means, this is the sample means from all possible samples of a specific size that could be drawn from a population. It's going to have its own shape, mean, and variability. Okay, variability, here's my standard error. And so if I go through and I say, okay, here's IQ scores. Mean of 100, standard deviation of 15. I know because it's an artificial distribution, it's something that we've created, but we know that's a normal distribution with a nice smooth distribution here. But I can't ever assess, and let's say it's everybody in the U.S. Let's say everybody in the U.S. I'll never be able to give all residents of the United States an IQ test, right? But what I can do is I can create a sample, right? And so I go through and I can create a sample, and I got a sample of 30. And I find that the mean is 102 with a standard deviation of 15.6. Rachel, does this look like this distribution? Not especially, right? It's kind of funky and it's kind of gross, right? I mean, it's not terrible. I've seen worse distributions, but with only 30 individuals, I shouldn't expect my sample to have a nice distribution of scores because I only have 30 folks in it, right? But we've got our own mean, our own standard deviation, our own shape. But if I go through and I create a distribution of sample means of sample size 30, right? What I'm going to get is I'm going to get a distribution of sample means. And this is the distribution of the average IQ score for all samples of 30 that could be pulled from the population. And I find that the mean of my sampling distribution, or the expected value of the mean here, is identical to my population mean. Okay, and have my standard error here. This is the standard deviation of this distribution, and it tells me how much I can expect, how much on average I should expect samples to jump in terms of average level from one to the next. I can use this as a measure of the expected precision of my individual estimate. I can use it as an index of how far I expect any randomly pulled sample to fall from the actual population mean. So we've got 3 different distributions, and what we want to do is keep these separate, be able to move back and forth flexibly with these. Okay. Questions about this? All right, cool. Let's do this. Let's stop right there. Let's take another 10-minute break. Let's be back at, we'll call it 4:45, and then we'll go through. You got like a mustache. we'll take a little bit longer break. Yeah, come back at 4:45, and we'll sort of push through sort of the rest of it. Again, if anybody needs to take off, Brittany, I know that you said you had a lab meeting. Go through, bail. I'll stay through, finish up for the rest of the time, but we'll record it all, so you'll be good to go. And so anybody else too, if they need to. All right, cool. All right, folks, we'll see you in a bit. Okay, now we're back on track. All right, so we talked about our distributions, right? So we got our population distribution, our sample, and our distribution of sample means. Why this is important, kind of tying this all together, is when we think about primary use of our distribution of sample means, what we're trying to do is find the probability of some randomly selected sample demonstrating certain characteristics based on some assumed model. Okay, so I'm assuming, and sort of we're using model very broadly, I'm assuming that something is in the world. I'm making some guess about the parameter of some population of interest. And so what we start to use our distribution of sample means is to start to identify the probability of selecting a sample with certain characteristics relative to what I assume the population should be based on sort of my theory or sort of my hypotheses, whatever, right? And so the question is, what we're doing here is asking what the probability of randomly selecting some sample with mean M, assuming a normal distribution with certain characteristics, okay? And the way we do this, again, we had gone through and calculated z-scores for individual score, or z-values for individual scores. We can use the same sort of type of formula to start to go through and calculate a z-score for sample means. And what I can do is I can start to identify the probability associated with a specific score to identify and locate and pinpoint the probability of randomly selecting a certain a sample of a given set of characteristics. Okay, so if I assume that the population that height in the general U.S. population has a normal distribution, and I assume that the average height is 68 inches. What I can do is, based on some assumptions, is I can start to calculate the probability of randomly selecting a sample of size 50 having an average height of, say, 63 inches. And I can start to make a determination, would it be likely for me to do that? Is it unlikely for me to do that? And then based on that determination, sort of start to draw inferences about the true height of the population of people in the U.S. Okay, so my Z statistic here, same setup. I've just got my sample mean minus the population mean divided by a standard error estimate. Easy peasy there. Okay, and so what I can start to do is I can start to identify the probability of obtaining a sample with some certain characteristics. So let's say I've got I know that SAT scores form a normal distribution, mean of 500, standard deviation of 100. Okay, and so what I can do is I can start to calculate the probability of selecting a random sample of 10 students with a mean SAT less than 440. Okay. I could also go through and let's say I want to look at the likelihood of selecting a random sample of 75 students with an SAT less than 440. So which of these, sort of based on what we know about standard error, so we basically have the same question, except in this situation we've got a sample of 10. Here we got a sample of 75. Which are we more likely to find someone with a sort of quite a low score, draw a sample with quite a low score, the sample of 10 or the sample of 75? What do you think, Brittany?
With like a low score?
Yeah.
I want to say a sample of 10.
Yeah, right? Because I'm going to have more variability here, right? So the probability of getting a random sample with a particularly low score, much more likely if I have lower sample size than if I have a larger sample size here. Well, what we can do is we can start to go through and attach specific probability values here, okay? So, always important to remember, if we see a pattern of data, right? If we see differences, we collected a sample with a mean that's different than our null value or what we might expect, several different possibilities, okay? One, pattern that we're seeing is a result of some systematic factor that reflects true effects in the population, okay? So let's say that I go through and I know that in the general population, IQ scores have a mean of 100, okay, but then I go through and I get a random sampling of doctoral students in psychology, and I find that average IQ score in that sample is 110. Okay. Now, how do I understand that? Right. Well, one possibility is that this pattern, this higher score on IQ evaluations or IQ assessments that I'm getting in doctoral students just reflects the fact that doctoral students, on average, by self-selection, tend to skew higher in terms of intelligence than your average person, which makes a reasonable amount of sense, right? So what we could get there is some difference that reflects true differences in the population. We're comparing the population of just the general population and the population of individuals who successfully are accepted into a doctoral program in psychology. It makes sense that these are distinct populations and that they might not have the same mean value for performance on IQ exams. So what we could see is an actual difference. But it's also possible that the result is just chance fluctuations, right? In actual fact, the population of individuals who get into doctoral programs in psychology actually, on average, have the same level of or the same performance on IQ tests as the general population. The difference that we're seeing is just random fluctuations. Robert, for a billion points in your immediate PhD, what do we call that? The difference between sort of my sample and sort of what the actual population parameter is.
Sampling error.
Yep, it could just be sampling error, right? Maybe what I've got is that sort of I see my sample of doctoral students have a mean of 110 on this performance, but in fact, the actual population parameter for performance in doctoral students is 100, right? And I've got some sampling error. I didn't do anything wrong necessarily. I just happen to see a difference in sort of some deviation between the true population parameter and what I actually got in my sample. So what I could be seeing here is just flat chance fluctuations, right? It could be that sort of the pattern that I'm seeing is a consequence of some systematic bias in my methods or violations of my underlying statistical model. Okay, maybe I'm assuming that maybe I don't have a representative sample. Maybe I just have a really poor sample that's biased, or my methods aren't good, or my measurements are terrible, or some other such thing. Or it's possible that maybe what I'm looking at doesn't follow the distribution that I think it does, right? And what happens if I have violations in my underlying statistical model, right? If my assumed distribution doesn't actually follow the distribution of what I'm actually looking at, what kind of distribution do we have? Oh, this is Rachel's favorite joke. It's a paranormal distribution. Oh, no. Okay, right? We forget about this. We can't go through and sort of divorce our methods from our tests, right? If someone says, oh, we've got a sort of a difference X, Y, or Z, what does this mean? I don't know. I have to check out the methods. I got to make sure the methods make sense, that the sampling strategy makes sense, that they've done things right, because otherwise, I don't know, right? And so what we do is we try and look at null hypothesis testing as a set of procedures that to try and facilitate our statistical inference, to try and evaluate sort of whether or not the data that the effects that we're seeing are due to real effects across populations, or whether or not they're just chance fluctuations, right? It's just random error and things like that, right? But again, important to remember that there's no test to tell me whether your study has good methods or not, right? There's no statistical number. I don't have a quotient that tells me whether or not what you did in terms of your study makes sense or is reasonable, okay? We need to go through and systematically evaluate the methods and be careful in looking at that to see whether or not our methods make sense. And again, when we're going through and running our data, sort of looking at our presumptions and our procedures, making sure that we know what the statistical assumptions of our test are, and making sure that if we do have violations, that we don't, that those violations aren't something that's going to negatively impact, at least to a certain degree, or to too much of a degree, the inferences that we can draw from our data. Okay. Otherwise, paranoid, they're going to get rid. Like running jokes. Right? There's a catchphrase comedy here, right? All right. So thinking about null hypothesis testing. Null hypothesis testing is a procedure that we use to try and draw inferences about some unknown population value based on some sampling data. Okay. So if we assume that a population has some mean, right? What we're asking with our hypothesis test is what's the probability of drawing a sample that has specific characteristics at or more extreme than the one observed in our data, okay? If we determine this to be a low probability, then we would say, okay, that the sort of data are probably falling in line with what we would expect under our null hypotheses. If it's very different, though, what we would typically do is conclude that likely the population from which this sample is drawn actually has some different parameter than what was expected under our null hypothesis. So let's say we have, has anybody done rat stuff before? Any animal lab stuff?
I've done stuff with like lions and tigers, but not.
Oh, look at the humble brag coming out like, oh, I don't know about your rat business. I've done some stuff with lions and tigers, no big deal. MBD, right? Okay, so let's not say let's say tigers have some like let's not that screws up my example. But okay, let's say that we're doing rat lab stuff and we've got some strain of rat. It's a genetically pure strain of rat, and we know that rats of this genetic strain have a certain weight. Okay, and we know that rats in this population have a weight of, let's say, 400 grams or something along those lines, right? What we can do is we can go through and let's say we pull a sample from this population, right, of known value, and we give this sample some sort of treatment, give them growth hormone or do something like that, right? This has gone now from a sample of rats of a known population. Now these rats represent a different population, right? This treated rats represent the population, a hypothetical population, as Erica noted before, of medicated rats. Now, we don't know what the population of this hypothetical population of medicated rats, we don't know what their weight is, right? It's some value. But what we're trying to do is we're trying to see if get some information about the expected weight of this medicated population of rats based on the treated sample that I've collected here. Okay, this is an unknown. We don't know. Okay, and so Erica, let's say my treated rats weigh considerably more. Let's say they weigh 500 grams. What's my best guess for the population weight of my medicated rats? It's 500 grams, right? And what I can start to do is I can start to go through and say, let's assume under the null hypotheses that my medicated rats, the average weight of my medicated rats is 400 grams, right? What's the likelihood of randomly getting a sample of rats that have a mean weight of 500 grams? Now, if I determine that this is a likely event, they're like, oh yeah, we'll see sort of expected fluctuations. Then we say, well, maybe this treated sample, maybe this unknown weight actually is 400 grams. It's not unusual to get a sample of rats that have a mean of 500. So yeah, it's weird, but it's not that big of a deal. Then we could say, yeah, maybe there's no difference in these two populations. But if we say that this is very rare, like, yeah, if the true population weight of medicated rats is 400 grams, it's exceedingly unlikely, if that's the actual parameter, to pull a sample of with a mean value of 500. Then we would start to say, okay, it looks like we have evidence that maybe whatever treatment that we did here has caused some sort of impact. Okay, so again, remember that anytime, Natalie, are we ever really interested in our sample? Exactly. Okay. So when we're talking about hypotheses, our hypotheses are always about a population. They're never about the sample. I don't need to run a statistical test to see what the mean of my sample is. I just look at my sample and know what it is, right? Is that sample different than 400? Well, yeah. I don't have to do a fancy test, right? What we want to do is run some tests to see how likely it is. If we assume that the population weight is 400, how likely it is for us to how likely would it be for us to get a sample with the characteristics that we found, assuming that they came from a population with a value of 400. Okay. Questions about this? All right. So let's run through an example here. So we're going to say the researchers believe antioxidant supplements may reduce and possibly reverse age-related cognitive decline. So what we've got is a sample of 25 individuals aged 65 or over and have them take antioxidant supplements for 6 months. Participants given known neurological tests to assess cognitive functioning. Scores for this test are known to be normal in the population, with adults 65 and older scoring a mean of 80 with a standard deviation of 20. Okay, so we know what the population parameters are sort of for just the general population of adults. Okay. Previous psychometric research suggests a change or difference in scores exceeding 10 holds practical relevance. Okay. So we know what the parameter or what performance looks like on this cognitive test in adults 65 and older. Okay. Who, though, Allie, so I've gone through and I've taken a 25 older adults and I've had them taking antioxidants for a period of 6 months. Are those individuals now representative of the larger population?
No.
No. Well, they might be, but they're a different population, right? They're a population of individuals who have been taking antioxidant supplements. What we're interested in is whether or not the hypothetical population of individuals taking antioxidant supplements score higher or differently on this cognitive test than the general population of older adults, right? So what we've done is we've taken a sample of typical older adults, we've given them some sort of treatment. Now they represent a different population. Now, whether or not that different population differs in terms of cognitive ability, I don't know. That's why we're doing the test. But they're by definition representative of a different population than the general population that they were pulled from originally. Okay. So what we're going to do with our testing is, one, provide a statement of the null hypotheses. This is predicting characteristics of our to-be collected sample. Okay, we're going to set the probability criteria for determining an interpretable effect. We're going to collect our sample data. We're going to calculate statistics. Then we're going to draw some conclusions about behavior of the population based on these data. Do not forget number 4, right? We're not just cranking out numbers just to crank out numbers. We're wanting to try and go through and glean something from the numbers that we've got to try and make some interpretations. Okay. So, number 1 thing, start by stating the hypotheses. And with our hypotheses testing, as we typically approach it, involves a couple of related hypotheses. We've got our null hypothesis, okay? And our null hypothesis is almost always going to say that there's zero association between some independent variable, some dependent variable in the larger population. We're going to say XY is not associated with one another. Basically, our manipulation has no effect on our outcome. Null hypothesis is saying that this population, or this new hypothetical population of older adults all jacked up on antioxidants, has the same memory performance as sort of our usual population. Okay? Our alternative hypothesis is going to make a statement about some association or some difference across groups or between an independent variable and dependent variable, again in the larger population. Okay, we're essentially saying that whatever manipulation we've done has some impact or some measurable effect on our outcome. Okay. Couple things. Our null hypotheses test is designed only to test the null. Okay, the only thing that we're actually testing here is whether or not the effect that we're seeing in our data is likely different than 0. Okay, we're not saying about how much it is in our traditional hypotheses test. All we're doing is just looking and saying, do we have evidence of some non-zero difference or some non-zero effect based on the data that we've collected? Okay. Also remember, and please keep this in your mind, anytime on an assignment you're thinking about writing I ask you to make a statement of the hypotheses. Remember that our hypotheses are always about our population, never about our sample. Okay. So as I'm going through, wanting you to think about who, based on the problem that we're working with, who's my intended population? Who am I hoping that this generalizes to, right? And sort of being clear about that. Having you tell me forces you to think about that, and so wanting you to be thinking clearly about generalization and who we think our data apply to. A couple things on our statistical models. Anytime we're using any type of statistical analysis or some type of model, we have some explicit assumptions about how the data that we're getting has been generated. Okay, if I'm looking at a difference, if I'm expecting my antioxidant, sort of my group of antioxidant elderly folks to be pulled from a distribution that has a mean memory value of 80, right? I'm assuming that basically what I've got is a sort of a bigger population, and I'm randomly selecting people that are going to fall somewhere around this 80 point. My sample may be a little bit higher, it may be a little bit lower, but basically under my null hypothesis, I'm assuming that I'm randomly selecting people from some population with a mean value of 80, okay? And when we're going through our hypotheses testing, in routine, the way we generally do this, almost always restricted to some point estimate of the null, right? That the difference is 0, that there's no difference, that there's no deviation, okay? It doesn't have to be that way. If you wanted to be gangster, you could say, well, this is the population, this is the difference that would make it actually be interpretable, right? So I'm not saying like, I'm not going to make make an assumption that the difference is 0. So I'm going to test against a difference of at least 5 or more. Because if it's less than 5, it doesn't make any difference, right? That's not how we typically run it. We could. That would be a much stronger way to go through and do things. But generally, as I said before, our hypotheses tests are generally testing whether or not something's different than 0, okay? But as we're going through and doing this, we have our null hypotheses and our alternate hypotheses. But if we get in the nuts and bolts and are thinking about this carefully, our tests and our methods generally involved a number of different sort of auxiliary hypotheses, auxiliary theories, a bunch of different assumptions about how those data were generated. And if I start to violate those, it starts to reduce my confidence that any effect that I found actually reflects a real effect. So some examples. Even with sort of some very basic sort of means-based stuff that we're doing, right? I'm going to say, okay, here's my null hypotheses, here's my alternate hypotheses, but I'm also assuming that my sample is representative. If my sample is not representative, whoever I'm trying to generalize to, it throws everything off. My model, my statistical procedures assume that I have a representative sample of the population of interest. My models assume that my sample is randomly selected. Do we ever randomly select anybody for anything in psychology? Nope. Very, very rarely, right? Our samples are samples of convenience, right? And so we're never, sort of our statistical model assumes like in a perfect laboratory, like in this sort of perfect set of situations, I have a representative sample from the intended population where all individuals have an equal likelihood of selection. Already, those are two things we know never happen in our studies, okay? We're assuming that the distribution of sample means is normal, which we have some robustness to that, but sometimes we have violations based on our methods. We assume that our model is correctly specified, that we've sort of actually got our stuff on target. We assume that we've got valid measures and that we're actually measuring the things that we're trying to measure. We're assuming our measurements are collected without error. And we're assuming that our hypotheses were generated prior to the evaluation of my data. Okay. If I start generating hypotheses after I've looked at the means and seen what my data are looking like, that's going to be a problem. Okay, because I'm going to go through and bias stuff. So remember that our confidence in our estimates and our sort of the extent to which we can infer information from these tests isn't just based on sort of the numbers that we're getting. It includes a whole list of implicit assumptions that we don't talk about, that we don't think about, but we need to, because as soon as we start violating these, the confidence that I have that I've found something that's reliable and replicable starts going down, 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 down. Yeah. Questions about this? All right. So, again, validity of our estimates, all predicated on us doing good research, solid research, that aren't just sort of our statistical assumptions, but also the methodological stuff. And if we start violating those, we start to become less and less confident that we can draw anything meaningful conclusions from our data. Okay, so always have methods going on, thinking about methods in the background. Okay. So for our example here, we're going to say that our null hypotheses is that the average memory score in our supplement, in the population of older individuals taking supplements, is an average score of 80. Okay, Robert, where did I get that average score of 80?
The average cognitive function score.
Yep.
Older individuals.
So essentially, what I'm saying here is that the average memory score in my supplement in the population of older individuals taking supplements is the same as the average score in older individuals in general, right? I'm essentially saying that supplements have no impact. Okay, so I can say here, this is stating it in statistical notation. In words, I might say the average cognitive functioning score in population of older individuals using herbal supplements is equal to 80. Okay, so here I'm just identifying my intended population, or the population that I'm trying to draw inferences about. Okay, alternative hypotheses that the average cognitive performance is not equal to 80. It's just some value that's different than 80. In words, average cognitive functioning in population of older individuals taking herbal supplements is not equal to 80. Okay, but again, please focus on sort of here when we're stating our statement of our hypotheses. I'm explicitly telling you who I'm trying to infer information about, and who I'm trying to infer information about is this population of older individuals, hypothetical population of older individuals who are taking these supplements. If I could take all older individuals and have them take weekly supplements, this is who I'm talking about. I can't do that, so what I'm going to do is I'm going to take a sample of older individuals, have them get on a supplement regimen, and then try and infer something about the hypothetical population from that sample. Okay. Second thing we're going to do is we're going to set our decision criterion. Okay. This is going to be the probability of obtaining the sample data, assuming that the null hypothesis is true, that I'm going to use to start to make inferences on whether or not something is supported or not supported by my data. Okay, so assuming that the null hypothesis is true, assuming that the population of older individuals taking supplements does have an average memory score of 80, how far off do I need to see, or how unlikely do I have to get a sample before I start to say, it seems like these data were not pulled from a population having a mean score of 80, okay? And what I can do is this is completely determined by me, okay? If I go through and I start to find sample means that are much different from the proposed population mean, a couple of different things. I can interpret this as sort of these data are incompatible with my model, because my model assumes a mean value in the population of 80. If the sample that I pull has a value that's so far different from that it would be very, very unlikely to be actually have been pulled from a population that has a mean score of 80, then I'm going to start to say that these data appear to be incompatible with the null hypothesis, right? Or it's possible that that I have some violation of the assumptions of my underlying model. Okay, so either it seems that if I if I'm playing by the rules, right? If all my assumptions are correct, and so I've got good data, and I find a sample that's very, very different than my assumed population, the mean of my assumed population, I would start to say that these data are incompatible with the presumed score of 80 in this hypothetical population. But it could also mean that I've screwed something up, that I've got some problem with the underlying assumptions of my statistical model. It could mean that I've collected a biased sample, or it could mean that sort of there's that I don't have a random or representative sample, or it could mean that I'm actually not working with the distribution that I think I'm working with, right? My null hypothesis test doesn't tell me whether or not I violated these assumptions, or whether or not I've got something problematic in my methods. I have to be thinking about that and evaluating that carefully. Okay. So this is if we've got something that's different, right? But let's see that my sample means are similar to my hypothesized mean, right? Let's say I assume the population of older individuals taking herbal supplements to have a population mean cognitive score of 80, and I find that my sample has a score of 83, I might say, well, looks like it's not 80, but it's not different enough for me to conclude that it's probably super different. And I would say, well, these data are generally compatible with an assumed population value of 80. And so, I'm not going to say that these data are saying that individuals with older individuals with who have been taking supplements might not have different scores on this measure. I'm just saying that I don't know. Sort of my data aren't conclusive. My data aren't able to say whether or not these are different or not. My data are never saying that the null hypothesis is true. It's not saying that, yes, the population of older adults taking supplements absolutely do have a mean score of 80. It's just saying that these data, at least the data that I've collected, aren't compatible with sort of that proposition. Okay. So our null hypothesis test tells us whether our data are unusual, but it doesn't tell us that anything about the model or any aspect of the model is correct. That's something that I have to go through and think about and evaluate on my own. Okay. So what we determine as unusual, usual, that threshold, this is determined by my alpha level. Okay. This is where we go through and define our critical regions, assuming this is the distribution that we should see. How far out do we need to get before we start to say that these data are not consistent with our null model? Okay. So again, our alpha level is going to give us the probability of obtaining data that are probable and improbable, assuming that the null hypothesis is correct. Okay. All right. So if these are our supplement data, okay, this is my distribution of sample means, assuming that my null hypothesis is true. Okay, assuming that the population of individuals, older individuals taking supplements, actually does have a mean value of 80. This is the expected distribution of all possible samples of size, however big my sample is. This is what it looks like. Okay. And then what we do, if we say alpha equals 0.05, what we do is we start setting up a critical region. Okay. So if I find a sample that has a score that exceeds these points, what I start to do is I start to say, yep, it seems like this is unlikely given the data. If it doesn't exceed those points, I say, well, it might not be exactly what the hypothesized value, but it looks like it at least is compatible if the population from which this sample was drawn actually does have a value that's consistent with my null. Okay, so we've got our critical regions out here and our expected value, all this stuff here. This is stuff that we would say is generally compatible with the data. Let me see. Okay, we'll finish up here. Most basic scenario that we've got are going to be our z-tests. Okay, these are going to be z-tests are going to be sample data that we go through and collect and compare against some known population parameter. Okay, in the hypothetical example that we have set up, okay, we're saying that we've got a small sample of older adults who we've had on a regimen of antioxidants. And what we do is we measure their score on some assessment that has a known value in the population. So we know, so we're thinking about this as kind of like a cognitive achievement test or something like that. We know in the population of older adults what the mean of the population is and what the standard deviation of the population is. If we know the mean and the standard deviation in the population, we can go through and use a z-statistic. Okay, z-statistic, pretty easy, straightforward. Our confidence interval, just the same as we've been doing before. This is our sample mean. This is our critical value. This is the sort of our level of estimation, and this is our standard error. Our z-statistic, our z-score, again, is going to give us the location of the position of our sample mean relative to the distribution of sample means, assuming the null hypotheses. Okay, and so again, my test here, just what we'd had before, sort of my sample mean minus my known population mean divided by my standard error. Standard error for my z-test is going to be the population standard deviation divided by the square root of my sample size. Okay. So just as we're going through and looking at this statistic, some things to keep in mind. Again, if I'm looking at my formula here, my numerator, this is just giving me the distance between my sample and the assumed value under the mean, right? So if I assume that older adults using supplements have the exact same cognitive performance on this assessment as older adults in general, then I would expect that to be very small. Okay, so this is my observed difference. My standard error, this is what I expect between randomly selected samples under the null hypotheses. Remember, my standard error is my standard deviation of my sampling distribution, right? If I were to pull samples of 25 from the general population of older adults with a mean of 80, do I expect those means to always, each one of those samples to always equal 80? No, they're going to jump around to some extent, right? What my standard error does is it tells me how much do I expect those to jump around. Okay, so Allie, if I expect on average sample of 25, that I expect sort of the average sample cross replications of size 25, I expect means to jump around by 4 points, and I find that the difference between my value under the null and the sample that I got is 4 points. Is that a strange value? No, it's about what I would expect, right? What if I find that I get a deviation between what I observed and what I expect? If I get a difference of, say, 15, and I expect on average sort of my sampling distribution estimates to jump around by 4, does that look, is that start to look like a bigger difference? Yeah, right. So again, if we're looking at this test statistic, again, try not to think about these formula as just something that I need to plug numbers in to get a value. Look at them and try and understand, again, what we've got here in the numerator is what the deviation between my null value that I've seen versus how much I would expect just based on sort of random sampling error and distribution. And if what I observe is a lot different than what I would expect just based on normal jumping around, I'm starting to get much more evidence that maybe the population of older adults taking supplements has some mean cognitive performance value that's quite different than the general population, right? But if what I'm seeing in my sample is about what I would expect just based on regular jumping around, then what I'm generally going to say is sort of in general expecting these data to be fairly compatible with the data that I'm, with what would be expected if these individuals were polled from a population with a mean value of 80, okay? All right, we'll stop there. You guys, again, are fantastic. Thanks for hanging in there, and thanks for giving me a little bit of flexibility on our start date today. Any questions about anything before I turn you all loose to sort of get some much needed rest and relaxation?